Okay, hello. I would like to welcome you to the class on numerical optimal control, and my name is Moritz Diehl, and I will just show you in a minute how it will all be working. This class is intended for self-study, that's why we record all these lectures. And it is quite mathematical, as you might notice already from the fact that we do it mostly blackboard-based, but it's very much application-driven. So we are very much driven by real-world applications, by people that want to control wind turbines or combustion engines or airplanes or robots that navigate through human environments, or maybe even such things like how to best vaccinate or to best impose restrictions on populations. So all these things would be optimal control problems in some form or the other. And the intended audience is engineers and scientists, and also mathematicians and computer scientists. Yeah, so both applications people and method people, let's say, mixed together, and it's relevant for both sides. The method people want to actually develop new methods. I'm partly a method person, but the applications people want to solve real world problems, and methods people like to sometimes look at real world applications, and applications people like to sometimes listen to the latest numerical methods and see how things are getting more efficient when you use the right methods and so on. So numerical optimal control, as the name already says, there is a field like optimization on the basis of it. Yeah? So optimization is one pillar of it. And optimization is a very big, thriving field in the mathematical, in the numerical mathematics community, with lots of engineering, computer scientists also in this community. And it's developing wonderful computational methods to minimize objective functions or maximize, we minimize in this class, subject to constraints. So the field of numerical optimization is one pillar. And the other pillar of this class is dynamic systems. So both are fields that you might already have heard about. But together, you need to know a few things from each field, and then you can bring them together, and that's what we will do in this class. Yeah? So optimization on the one hand, dynamic systems on the other hand, both have quite a mathematical flavor. I would say in the mathematics community, there is people that are experts on dynamic systems, and there are other experts on optimization, and then there are also experts which are really experts on optimal control, and they need to know about both. Yeah? So this is the big picture of this class. It's heavily based on a manuscript that I recommend. So it's this book draft. It's also entitled Numerical Optimal Control, and we follow chapter by chapter the contents of this book. So in a nutshell, a dynamic system is something that evolves over time, right? Could be if I throw something, it's flying, right? Could be the motion of a car. It could be the development of infections of a disease over time. That's the dynamic system part. But then it's all about optimization, and that is how to choose the inputs so that we can optimally achieve some aim. Yeah? So for example, if I drive a car, I might want to drive it as fast as possible around the corner. Yeah? Or if I want to avoid infections, I want to avoid them with the lowest possible cost. And what is now interesting about this dynamic system interaction with optimization is that you can typically have actions that you take in the first second, or in the second second, or in the third second. So you have many different time instances, and at each time instant you can choose your controls. Yeah? So think of the steering wheel, left or right, and you can actually decide when to move it to the left and to the right. And by this, you can actually reach lots of places in the world, every place. So there's a lot of choices. And so optimization has an incredibly large search space, if you think of it, right? So you could not say that you want to randomly try out all possible combinations, because already if you take the first 50 seconds, then you have already 10 choices for each second, then you would have 10 to the power of 50 possibilities, right, to explore. So this is impossible to randomly explore. And so that's why people use very often derivative-based techniques, which are also the focus of this lecture. Yeah? So maybe I should already say at the very beginning, the focus of this system, of this class, yeah, is continuous state spaces and control spaces and differentiable functions. So these two ingredients, I think, are important to keep in mind. So continuous is actually a precondition for differentiable functions. But we want to use derivative-based optimization on this part, so we need to restrict the dynamic system classes that we can look at. In the introduction, I thought I give you a bit of an overview of what dynamic system classes we have. And then afterwards, I give you a bit of an overview of optimization algorithms. So let's start with the dynamic systems. So we are now in chapter 1, and maybe I should first give the headline. The headline is chapter 1. It's the introduction. That's where we are in. And I start with the section 1.1, which is about dynamic system classes. And I decided to start with this overview of dynamic system classes because I want you to be aware of the fact that dynamic systems are much more than what we cover here, continuous state spaces and differentiable functions. So there could be other things. And so please be aware that you need to recognize what type of dynamic system some practitioner approaches you with, for example. And only in some cases you will be able to apply the methods from this class, and in others you will apply things from other classes, or maybe need to adapt some of your methods. Okay? So I thought I would just go one by one through the dividing lines in the field of dynamic systems, and then already give you an idea of what is the dynamic systems that we are most interested in. So the first dividing line, which is also the structure of this class, I want to tell you is about continuous time versus discrete time. Yeah? So it's the first dividing line is continuous versus discrete time. And it's quite natural to have as a distinction. Continuous time is nearly everything that we are familiar with in physics, physical laws, chemical laws. Most things we write down in terms of differential equations that evolve in continuous time, right? So when I throw a chalk or when I drive a car, then this is continuous time. On the other hand, nowadays in the time of digital computers, or also in some abstractions, we are very much familiar also with the notion of a discrete time system. For example, every clock of a computer, there is a new state in this computer, right? And you could also think of a sample data system. So if you take a camera image, every so and so many milliseconds, like 25 times per second means every 40 milliseconds, you will take a camera image, and you might have a dynamic system that you want to somehow describe as evolving camera images. Yeah? And in these cases, you would have discrete time systems. Another example could be something like the daily stock market returns or something. That's very often modeled as discrete time systems, even though stock markets evolve over the day as well. But if you want to look at a year, then maybe you just look at the daily end rate of every day, for example. Yeah? So continuous time is clear. Discrete time is also clear. In discrete time, we have an index k. And maybe I should say that our notation is that in continuous time we have a state x t, and t is, x of t is typically in some state space. Yeah, for example, here a real valued vector space, but t is a real number. Yeah? So that would be our notation for continuous time. And for discrete time, we would typically have states that we still have in some state space that might be nx dimensional, right? But we give them a lower index just because I find it, it's less symbols to use, right? So some people put the discrete time index also into parentheses, but we don't. And k is an integer. Yeah, so k typically is 0, 1, 2, and so on. So this would be our discrete time system. And these are the two notations that I would like you to already be aware about. That's our way to look at continuous time systems and discrete time systems. Index t for continuous time, index k, but in integer, is for discrete time. So I already somehow implied what I said before, namely that we are mostly interested in continuous state spaces. But this is a special case, and I want you to be aware of the fact that it's not the only possibility. So I want to make the dividing line between continuous and discrete state spaces. So you can have continuous versus discrete state spaces. And a continuous state space typically is something that we would describe by real numbers. Yeah? So like x element in Rn. Yeah, so somehow our state, I omit the index because it would be either applicable to continuous or discrete time systems, so I don't need the index here, right? I just want to say it's in Rnx, for example. Yeah? And there could be also discrete state space, and discrete state spaces would typically be something in integers, right? Or in these would be the integers, right? Something like this, yeah? 0, 1, -1, yeah? So the integers, possibly different components, that would be a discrete state space. And of course, discrete state spaces can be subsets of that, right? Very often it's 0, 1s, and so on. The same for, of course, continuous state spaces. You could, on the continuous side, also think of manifolds, like, for example, things moving in rotation space. Then it's sometimes better not to describe it really by real numbers, but somehow adopt the language of manifolds. So you can also use differentiable manifolds. That would still be on this continuous side. And on the discrete side, you could, decode everything in this form, but you could also think of positions in a game and so on, right? So, if you think of a chess game, yeah, one picture with all the figures located shows you everything about the game, right? It's the state of that game. So you can have continuous or discrete state spaces, and you can also have mixed forms of both, right? So if you mix them, so if you have this and this together, then we call it a hybrid state space. And some things where we would mix these two is maybe think of some already mechatronic system where you have a digital computer interacting with a continuous time system. So, for example, a chemical plant where at some point a sensor would give an alarm and then take some strong actions. So then the fact if this sensor has given an alarm or not, would be a discrete space. Yeah, so it could be already alarm state or not alarm state, while the continuous part could be temperatures in your vessel or such things. Yeah? So things can be also mixed. I should already say that in this lecture we will really focus on continuous state spaces. So I make the box around this. maybe I should also stress before, on the times we are agnostic, so we do both, right? We even start with discrete time in the first chapters and then go to continuous time later. But on the state space, we only have continuous time. And please think, a state is always what you need in order to, so to say, predict the future of the system. Yeah? The state is the memory of your dynamic system, so to say. Okay. I should say that some interesting discrete or some interesting hybrid systems are also happening when you think of billiard balls, for example, or any system that has some dynamics which has, you throw a ball against a wall, right? It's getting reflected, and at the moment that it's reflected, the velocity has really a jump. And so you can describe these things also as a special form of hybrid system. And some of the methods from this class can be extended into treating such classes. But generally, they are more difficult, of course, and the continuous state space is really the beautiful area we would also have convex optimization problems and so on. On this continuous side, I think I want to make another distinction which we should be aware of. And maybe we can move the camera a bit more. Yeah, don't know. So this other distinction is actually in continuous state spaces you could have, as I denoted here, finite dimensional spaces where you just need to know a few numbers, for example, position and velocity of some moving body. They describe how this body will evolve, right? In 3 dimensions, it would be 3 positions and 3 velocities, so altogether 6 numbers, and then you can describe the motion of a body. Yeah? But there are some other cases where we would have infinite dimensional state spaces. I want you to be aware of the difference. So we have finite versus infinite dimensional state spaces. Yeah, these would be continuous state spaces anyway. And if you think of an infinite dimensional state space, we would typically think of a distribution in space, for example. Yeah? So if you think of just this room here, this room has you would say a temperature, but actually the temperature is not one temperature, but it's different at every point. So I could measure it here, or here. So I need to know the temperature profile as a function of space. And that would, if you think about this as state space, it would mean that I have a temperature at every single point in space. Yeah? So that's a function. And this function I need to know if I want to really know in what temperature state this room is. And then probably I would also have to know the motion, the current motion of the air, because, there is air moving in this room. When I walk, it will mix a bit, and this will mix the temperatures. So if I want to really describe in a very detailed form the temperature distribution in this room, for example, because I want to have it well climatized, the most detailed model would be something that has both velocity of the air and temperature of the air as a function of 3-dimensional space, and this for every single time point. Yeah? This would be obviously continuous time, but it would also be a continuous state space, but it would be an infinite dimensional state space. Yeah? Because on the finite, we would have x element in R and x, as I said, finite dimensions. But here, it could be something x element in some function spaces, for example, something like continuous functions, right? From some interval, let's say some omega to R, for example. But this could still be many dimensional. Yeah? Maybe I call it some n, yeah, doesn't matter. But so the x itself would be in function space. Yeah? If you want to visualize it, I think it's one way is to think here of the dimension index, right? So 1, 2, up to nx, right? So, and I could visualize it, each component is some number. So this would be maybe a position, and the last 2 could be a velocity. And together you can just visualize your state as nx numbers, right? if you think of a continuous state space, and I just have here omega being maybe the interval from 0 to 1, so that's the domain of the state space, then I would have here a domain, 0, 1, and my whole state is not represented by nx numbers, but by infinitely many numbers, namely by a whole temperature profile. And this would then evolve in time. And if you want to treat these things with methods that you learn in this class, there is a way to deal with it, but the way is actually to discretize in space before you do something. So you can do something by space discretization. Yeah, so you discretize in space. Discretization. And then you get something that is more like the previous one, but typically very high dimensional. So think of, I will just represent the same state with a discretized form. Right? So this could be the same state as before, but now with nx numbers, and nx is then very big. Maybe I should already say that the transformation of a continuous state space into a discrete, of an infinite dimensional state space into a finite dimensional state space is called the method of lines. Typically, we get an ODE afterwards from a PDE. So here's the world of ODEs. And here's the world of partial differential equations, PDEs, or even more complex equations like integral differential equations and so on. But typically an ODE is what describes a system in finite dimensional state space, and a PDE, a partial differential equation, is very often describing motion of in infinite dimensional state spaces, for example, the fluid flow in a room or in the atmosphere. Yeah, so when you have weather forecast, it's all based on PDE discretizations in some form. But we need to be aware of the fact that there is a step between the continuous representation of the infinite dimensional function and the discretized form, which involves some numerical errors and so on. Okay, so the bottom line is we are here. We are interested in finite dimensional state spaces, and I have already sketched a way to go from infinite dimensions to finite dimensions. Of course, very rough sketch only. Yeah, I think it's now time to talk about controls. Until now, I didn't mention the actions that we have available. But controls are what we can influence. And if you think of my blackboard, I think this is a nice example to just look at it. So if I move it here, the state would obviously be the position of this blackboard, right? I can move it up, I can move it down, and I cannot move it. So this is a controlled dynamical system, right? And so now the question is, what is the control space? And if you think of this blackboard, it's actually, I press harder, it won't move faster, right? So it actually is only going up or down with fixed speed. I cannot really influence it, or it's not moving at all. So for this blackboard, it has exactly 3 choices: up, down, or 0, so to say. Yeah? So this is a finite choice. And for a general dynamic system, I could have also infinitely many choices. So for example, in my steering wheel, I can typically move it continuously, right? So I want to make you aware of continuous versus discrete control sets. Maybe I should also say that Yeah, we would typically say there is a control, either in continuous time or in discrete time, but we call it U. And U is element in some space U, or some set U. And U could be a subset of Rn U. Yeah, typically, I like to use this n with a little index U in order to denote it's the dimension of the U, right? Or it could be subset, so that's the continuous. Let me move it to the left side. So this U would be a subset of Rn U. And on the discrete side, it could be a subset of Z n U. Yeah, and simplest case, for example, here, as I said, could be just the set -1, 0, and +1, for example. And here, it could be, for example, -1 up to 1, the full interval, right? So these would be continuous and discrete control sets. And I think I forgot one definition. When we talked about state spaces, I think in the manuscript we have a notation where we say X is element in big X. Big X is either a subset of the real numbers or of the integer numbers in case of continuous or discrete state spaces. Okay. So you see already from this Blackboard example that very often actually you have these finite choices. And that's, I mean, whenever you have switches, right? So then you have only finite choices. But still, in many cases, we have so many of these choices, right? So even in digital control, very often you have a nearly continuous choice with potentiometers or such things, that very often this assumption of a continuous control set is not a bad one. And now mathematically, continuous control sets are extremely more easy to treat. So we typically restrict ourselves to continuous control sets. And I should say that, fortunately, there is, for discrete control sets, there is always some form of possibility to relax it. So you could, for example, relax this, which has only 3 values, to allow all these values, right? And then you know that the optimization problem can only become a better solution. And this helps you to get good algorithms to solve these integer problems. You can, of course, have hybrid systems, right, that have both discrete and continuous controls, and then you would have a hybrid control set. And I want you to be aware, for example, if you drive a car, you have lots of switches that you can press, right? In particular, for example, the gear shift. Yeah, the gear shift has, typically nowadays like 5 forward gears, right? You can choose either of them, but nothing in between. And you can choose the gas pedal continuously. Yeah? So there you see that you have already a hybrid control set. Both of them are decision variables. And it's, for this reason, interesting to know about hybrid control sets. And I should say that optimal control with hybrid systems in general, either continuous or discrete state spaces or continuous and discrete control sets. So then we call them hybrid systems. And that leads basically to some technology which is called mixed integer optimal control. So if you want to extend methods from this class into hybrid systems, that means either control sets or hybrid state spaces or both, then you enter the field of mixed integer optimal control. And I think it's interesting to know about that. We will not treat it really in this class, but it builds on technologies that we use in this class. So I think it's not out of reach for many people that follow this class to go into, in particular, the case of control sets being discrete is relatively easy still compared to the discrete state spaces, which are a bit nastier to treat. The reason is actually the convex relaxations that are easy in this context. Yeah, so now we have already covered quite a few of our dividing lines, but there are many more. And I think I want to maybe do a mini break here and go on in a few. Okay, so let's look at another dividing line between dynamical systems. And this is the difference between time variant and time invariant systems. So time variant is a system that depends on time explicitly. For example, if you want to describe the temperature evolution in this room, it will probably depend on the day time. Yeah? So from the outside there is an influence because it's getting hotter and cooler outside over the day. Yeah? Over the day it's hotter than in the night. So if I want to describe with some differential equations my room temperature, I need to take into account this external time-varying nature of my ODE. Yeah. On the other hand, if you think of some closed system that doesn't interact with the rest of the world, or you actually abstract from it, so you think of maybe the motion of the planets in our solar system, you would say they are probably not so much affected by outside influences that might be time-varying. And so you would say this is completely time invariant. And typically, when we have physical laws, they are time invariant, right? So many of the systems that we write down, they will be time invariant. Yeah? So maybe for an ODE, it would be the easy case is x equal being something depending on x dot. The derivative depends on x and on u and explicitly on time. That would be a time variant system, and the time invariant system is x dot equals f of x and u. So there is no explicit notion of time. And the interesting thing is that they are not so different as they seem. Yeah? So these two, once you take a nonlinear perspective on systems, they can be both transformed into each other. So most of our algorithms we will develop for the time invariant case. And that sounds like a restriction, right? Because that sounds a bit more general. If there's a trivial way when you have, let's say, if we would treat that, then it would cover trivially also that class, right, of time invariant systems. You just make the dependence on time redundant, so it's always not depending on time, but you theoretically have it. So that is very easy to, if you have such a system, a time invariant system, you could always frame it as a time variant system. But the other way is also true, and that's maybe less known. So if you have a time variant system, so you have a function that depends explicitly on t, you could also frame it as a time invariant system, and that trick I want to show you. This trick is actually including a new dynamics. So I have a clock state. I need to introduce a clock state. Maybe I call it C, just for fun, yeah, C of t. And we will actually let it evolve very trivially. So we just say C dot equals 1. So it's just counting time. And then we keep our ODE and we just say x dot is equal f of this f, right? Of x and u and c. C is the clock state. And this way we have transformed our time variant ODE into a time invariant system. So if you want to make it explicit, I would just say, let's define an x tilde. X tilde consists of the clock state and of an x. And we define an f tilde that depends on x tilde, which is actually this and that, right? And on u. And our ODE is then just x tilde dot equals f tilde of x tilde and u, and I forgot to define this f tilde, and this would just be a 1 here, and an f of x and u and c here, which obviously is a function of x tilde and of u, right? And you see that you can transform a time variant system into a nonlinear time invariant system with this little trick. And in that sense, it's not even a restriction if we restrict ourselves most of the time to this case. Sometimes things are time variant because it doesn't cost you much. Particularly when we look at linear systems, it makes a big difference if you have a time variant linear system. Yeah, that's very much nicer than a strongly nonlinear system after this transformation. Yeah? So for linear systems, maybe I should say you would have x dot equals a of t times x plus b of t of x of u for the time variant case, while you have for the time invariant case you have x dot equals ax plus bu. This already brings me to the next dividing line, which is actually between general nonlinear and linear systems. And this dividing line I think we should also be aware of. So let me just say linear versus nonlinear systems. And here, linear systems are typically the easier ones. Nonlinear ones are more general, obviously comprise the linear ones, but are also much more abundant in nature. So I basically gave the formulas already. So linear systems could be described by such a formula if they are time variant. They could be described by this formula if they are time invariant. Yeah, so these would be a linear time variant system, LTV. This would be a linear time invariant system, an LTI. And these LTI systems, they are particularly popular, and mostly because of the fact that every system that is not depending on time and which has a steady state in which you want to control it, you can basically by linearization transform it into something that is an LTI, a linear time invariant system. And then you can already describe it quite well in this neighborhood of your steady state. And so LTI systems are extremely popular because they are mathematically one of the most beautiful classes of systems and still complex enough to do a lot of science around them. So LTI systems, maybe I should just say LTI systems are the focus of a lot of control theory. Yeah? Much of control theory is about them. Are the main focus of control theory. And you might all be familiar with LTI systems, and you can either characterize them by matrices A, and please keep in mind they would be matrices in some spaces, nx times nx, and a matrix B that could be in nx cross nu, right? From the dimensions you see it. That would be one characterization, but it could equally be represented with a step response function, and that would be exactly as informative, and you could also equivalently represent them with a frequency response function, and we are all familiar with these Bode diagrams. So that's all the world of linear systems, or LTI systems actually. And one common error I see in lots of engineering applications of optimal control is that people somehow address a nonlinear system or a time-varying system, and then they try to apply the language of LTI system language, in particular frequency response functions. They are really not making so much sense for nonlinear systems, so we should be aware of that. There is a lot of things don't hold when we are in the nonlinear domain. Yeah? So for example, in nonlinear systems, when you increase the magnitude of your input signal, you will get a different, possibly different frequencies out, yeah? Which will never happen for LTI systems. So please keep in mind that LTI systems are beautiful, but they are just a subset, and a lot of the techniques that we learn, maybe in bachelor classes on control, they are really restricted to LTI systems. So we should not always use that language when we are doing nonlinear or time variant control. Yeah, I already used the word control quite a lot, but I think we should also be aware of the fact that there is a difference between controlled and uncontrolled systems, right? So many systems in this class will be controlled systems, like the car has a steering wheel, right? But for example, at the moment that your car is, for example, okay, this is not very recommended, but imagine that you drive across a cliff. Yeah? At the moment that you leave actually the road and you fall down, your car is an uncontrolled system. I mean, you can use your steering wheel, but it will not affect the trajectory of your car anymore. And that is also true for many technical systems. So even if I am able to control, let's say, my arm while I throw, at the moment that I, so to say, release the chalk here, I destroy it, yeah? It's uncontrolled. So we have controlled versus uncontrolled systems. And that's not a very mathematical challenge. I mean, controlled systems are just systems with controls, yeah, where we can distinguish actions over time, and uncontrolled systems don't have it. So we will treat both, obviously. Yeah, for uncontrolled systems, you could say the set of controls is just empty. So there's no choice to make. It's just always the same, yeah, nothing. Yeah? So for example, an x dot equals f of x. That could be an uncontrolled system, which is also time invariant, right? And so maybe I should also say that uncontrolled plus time invariant, if you have these two things together, basically like this, yeah, then you call it an autonomous system. It's just the language that is used. So when people say this is an autonomous system, please be aware it's typically not time varying and it's not having any inputs. It's just doing what it wants. For example, motion of planets around the sun, basically an autonomous system, we cannot really influence it, and it's not interacting very strongly with the outside world. Yeah, and you say a person is autonomous, basically a child is autonomous if you don't have to control it while it's walking over the street. You just let it walk over the street, you don't watch, you don't correct, and hopefully it's autonomous enough to cross the street without your interaction. And if you think of robots, I mean, a lot of work is now carried out about autonomous systems. They are actually those where people, so to say, don't interact. And basically at the end, the whole technical system with all the control systems and the digital logic together, they are making it an autonomous system, so where humans don't have to interact with it anymore. So mathematically, it's just, you could say, uncontrolled and time invariant. And controlled systems, as I said, are the ones that we usually think of. Maybe I should also say, if we add to this uncontrolled system a discrete state space, for example, a game, yes, then we would call it an automaton. It's like a typical notion of an automaton that's just acting in discrete time space according to its own laws and just producing a series of numbers with some algorithm that's automatically executed. I should say that in the world of control systems here, we will have some defining properties which are very well defined for LTI systems, so I think I want to mention them. And there is the notion of a control-level system. That's, of course, a specifically nice subset of the control systems. Controllable means basically that from any state, initial state, you can steer by choice of controls the state to any other state. Yeah? So that's in particular well defined for LTI systems, and you can try to generalize these definitions for other systems, but it's particularly well defined for LTI systems. And then there is a subclass that's a bit less restrictive, because this controllable means that you can do, so to say, whatever you want with your system, which is remarkable as a property, right? So even with a single scalar choice, for example, with some input of, for example, acceleration to a speed, to a system with two states, namely with position and speed, right? If you push it into one direction, and you can push it also in the other direction, you can bring it actually to every speed and position space. So if I say after 1 second I want to be at that position, but I want to have a reverse speed, I could get it by just going to that position a bit further maybe, and then bringing it back with extra force in the other direction, and then I can reach exactly that point in state space. Yeah? So that would be a controllable system. But there are some other systems where you can actually apply controls only to some parts of your system. But some other parts of your system, they are determined by autonomous dynamics, but fortunately they are stable, and so you don't care so much about them. And many technical systems are of that form, and so more general are the so-called stabilizable system. So controllable systems are subclass stabilizable systems. Yeah? So controllable are a subclass of the stabilizable systems, and they are a subclass of all control systems. Yeah? You might have control systems which are just, you can do something, but you cannot avoid that they might explode, for example. Let's hope that the corona pandemic isn't of that nasty form in the world, even though it might be that we apply our controls like vaccinations and lockdowns, but at some point they are not strong enough in order to avoid the explosion into a big tragedy. Okay, so I mentioned already stability. So this is a bit fuzzy if you want to talk about it in the general case, but I still want to mention that there is stable versus unstable dynamic systems. People at least use these terminologies. If you strictly want to define them, you can define that for LTI systems. Yeah, so you could say there is a stable LTI system. There's an unstable LTI system. It's very easy to characterize it by the eigenvalues of your matrix A. No problem with that. But once you have a nonlinear system, it's strictly not really easy to define what is a stable system. But what you could say, you can have stable fixed points. Yeah, yeah. More correctly, have stable attractors. Or fixed points. Yeah, so if, for example, if I look at an inverted pendulum, I think I have a stick somewhere here. So I could regard the stick as, maybe just for fun, an uncontrolled system. Yeah? So I don't apply any control. Here's my middle axis. And here at the top, I have a fixed point of my system. I mean, if I balance, now I do feedback control, as you see, but I can balance it, right? But at the moment that I stop balancing, it will just fall down. Yeah? So it's an unstable fixed point up there. So there is an unstable fixed point, but this is a nonlinear system, by the way. And if I have it hanging here, this is a stable fixed point. Yeah? So I don't need to apply my control in order to stabilize it or whatever. Right? So you see, for a nonlinear system, you cannot say this is stable or unstable. It's unstable up there and it's stable down there, right? If you would linearize it here, then this is a linear stable system. And if I would linearize it up here, then it would be an unstable linear system. So this is well defined. But for the nonlinear system as a whole, I couldn't say it's a stable or an unstable system. So that's actually badly defined. And more correctly, for nonlinear systems, at least, for non-LTI, I could actually think of stable attractors or stable fixed points. And stability, I won't give all the mathematical definitions here, but one interesting thing is that you can have stability, but you can have also asymptotic stability. And asymptotic stability is a bit stronger. Stability basically means that if you are close to the fixed point and you start close to the fixed point, it means if you prescribe some environment, some neighborhood around this fixed point in which you want to stay, then you can find another neighborhood in which you have to start in order to always stay in that neighborhood. And by making this possible choice as small as arbitrary, you basically have a kind of stability definition. And asymptotic stability, in addition, says that all these trajectories, when you start at least small enough in your neighborhood around the fixed point, that all of them converge to the fixed point. Yeah? So that's a stronger condition than stability of a fixed point. And there are others. I think, as I said, it's difficult to rigorously talk about stability if you don't define fixed points and if it's autonomous or not. I mean, for control systems, it's difficult to say it's a controlled, unstable system. You can somehow intuitively in the linear world, you can actually talk about it, but in some cases it's not making sense. But be aware, stability matters in practice, obviously, right? So you have stable and unstable situations, and they are typically around fixed points, or sometimes around fixed orbits. Maybe I should say one remark. This is something I find interesting. It's not related exactly to stability, but it's about linearity and nonlinearity. And this is a completely a remark mixing a lot of these things. So, periodic stable orbits. Yeah? They can really not appear with linear time invariant systems. Yeah? So they can be stable or unstable. You might have somehow marginally stable systems, but really an attractive cycle that is periodic can only happen, for example, for nonlinear autonomous systems. If you look at autonomous systems, you need nonlinearity in order to get some limit cycles. And then these limit cycles, they can be stable. Yeah? A typical limit cycle could be, for example, if you have, if you play a flute, right? You have the flute, you throw air into it, actually you blow air into it. Yeah? You have a certain position of your fingers and then you make, and at some point there comes a sound out of it. And this sound is a nonlinear periodic limit cycle, right? Actually, I can not, this is not a flute, but it's my hand, my mouth making a flute. So I can actually form my mouth, blow air, and I will create a periodic limit cycle. Really? A limit cycle, it's a sinusoidal motion of air. And this is a completely nonlinear phenomenon. Yeah? So I want you to be aware of the fact that these nonlinear limit cycles, they are inherently nonlinear. Couldn't mathematically appear for LTI systems. And when I speak, actually, what we do here, I'm singing, it's exactly the same. So this is nonlinear periodic limit cycles all the time. My heart beats. This is also a nonlinear periodic limit cycle. Everything that's periodic in nature is a nonlinear limit cycle. So in some sense, these periodic limit cycles are an interesting part of stability. So you could have stable periodic limit cycles. I think as extremely interesting part of nature, but I want to make you aware of the fact they appear only for nonlinear. I mean, okay. If you assume autonomy, right? For autonomous systems, appear only for nonlinear systems. So that's a remark I wanted to add because I find that quite surprising given the fact that so many other things are so well described by LTI systems, but all these nonlinear periodic limit cycles you cannot describe by LTI systems. Okay, good, but another dividing line, and that's something I think is extremely important to note. We typically think of deterministic systems in this class, but there is also the possibility of stochastic systems. Yeah, so the next dividing line I want to discuss is deterministic versus stochastic systems. And yeah, we will be mostly interested in deterministic systems, and that's everything that I've talked about until now is deterministic. But there could be some other settings where it's much more natural to talk of a system as being stochastic. Stochastic in the sense that you cannot predict the future at all because it's driven by some unknown noise. Yeah? And if you think of the foundations of physics like quantum theory, at the very bottom, our world follows stochastic laws. Yeah? So there's a lot of stochasticity at the bottom, which will actually translate into stochasticity happening in the world, right? On the other hand, deterministic systems bring us very, very far from not having systems at all. For example, right, if you think of the motion of planets, you can predict them over centuries in advance. Yeah? So you can already now predict that in 100 years there will be at some point the sun making the, there might be the moon moving before the sun so that we see a darkness over day, such things, right? So this could all be predicted by deterministic systems. But there are other situations, if you think already of weather forecast, you cannot really predict very well the weather in 2 or 3 weeks. And that you could model by stochastic systems, even though you could debate if that's stochasticity or chaos. But anyway, a very useful engineering approach to describing systems which you cannot very well predict is actually to model them as stochastic. A typical example is Brownian motion. So if you look at small particles moving in a glass of water, yeah, very small with a microscope, you will see them just drifting around. Yeah? Brownian motion, that's a typical example of a stochastic process. Random walk, we call it also mathematically. Yeah? So here, let's say Brownian motion. In mathematics, you would call it random walk, or in computer science. And for example, if you want to model stock markets, yeah, so like the development of stocks, then most often people would model it like a stochastic system. And many things we will model as stochastic systems. Also, a lot of estimation problems have stochastic system models. But then, if you have deterministic, it's like Newtonian physics, right? Actually, let me say Newton, but it's also even Einstein, right? Newton's laws of physics. So they lead to deterministic systems. A lot of other equations are actually deterministic. And very often, actually, we like to deal with deterministic systems. There is something that's a blurring between deterministic and stochastic systems, and that is chaotic systems. Chaotic systems are typically described as systems that are deterministic, they evolve in a finite state space, so in some portion of the state space that's not infinite, it's unbounded, but they are behaving practically like stochastic systems. Yeah? And this would be, for example, the weather PDEs. Yeah, if you would want to describe weather decently by partial differential equations, they turn out to have this chaotic property. And one very simple example is the Lorentz attractor. That's a beautiful system with only 3 states. It's an ODE, very simple to write down. 3 states, and it's having surprising behavior. And the interesting thing about chaotic systems, so they are somehow at the intersection of these two, so to say, but they are actually deterministic systems, but they are difficult to predict. And this Lorentz attractor, you can start the simulation, and after some time it has 2 circles in which 2 limits, so to say, 2 periodic limit cycles, but actually it swaps from one of the 2 into the other very often, and it does so with very unpredictable behavior, because the initial conditions are really, you would need to know them to many, many digits in order to predict, so to say, the switching sequence of between these 2 periodic attractors, so to say. And in practice, yeah, this is impossible. And numerically, I mean, you do errors all the time, so you cannot predict the behavior of that Lorentz attractor for many seconds in advance. So it's a beautiful example to study, and we study it in our first exercise. I think this is enough for today. I think I have to conclude here. And next time we will talk more about a few more dividing lines, and then go on with a lecture into the field of optimization. But let me first thank you very much for your attention today, and I'm looking forward to seeing you next week. Okay, let's look more at the dividing lines. And we just mentioned deterministic versus stochastic systems. And I want to make a remark that I forgot to say, namely that some systems are neither deterministic nor stochastic, but you would better say they are games. Yeah? Or in the sense that you would have one player. Like imagine chess, right? So that's a dynamic system. I can make some moves. So my controls is what I do with my figures every moment. But there is an opponent. He or she can also make choices. And typically they make their choices not randomly, right? It's not a random opponent, but typically they want to oppose me, to beat me, so they would probably take actions that are particularly bad for me, right? So they are really adverse players. And in that case, the best language to describe the system is not really randomness, but the better way is to model the adverse player as someone who wants to do as bad as possible to me, for example, right? Or in more general, has some different aim than I have. And then you enter the field of games, you would say. So this is game theory, where you have adverse players, or players which have other objectives than you. It's still somehow subclass of optimal control, you could say. And the connection gets even clearer if you think of one part of control theory, which is called robust control. In robust control, we want to actually design controllers, that means systems that decide on the control actions, that behave well still under very adverse circumstances. Yeah? So they are robust against bad behavior from nature in that case. Yeah? So for example, for all possible systems from a class, we want to still have a stabilizing controller. And so the field of robust optimal control is actually very similar to game theory, even though games you would typically think of discrete state spaces and so on. And in robust optimal control, you would typically think of continuous state spaces. But this is, let's say, mathematically very similar. Yeah? So you have an adverse player, could be nature, could be another person, that is actually not having your objective. Yeah? It's doing the worst thing for you, typically. So that I just wanted to add about the deterministic versus stochastic systems. Yeah. And now I want to point out another dividing line, and that is the difference between open loop and closed loop control systems. Open loop versus closed loop control systems. And if you think of this dividing line, of course, they only make sense if you have controls, but there is a big divide. Yeah? So open loop control systems are systems where you decide, before you actually run your process, you decide on the actions. So for example, in daily life, yeah? So you have a cooking instruction that says, for example, put your potatoes into a pot of cold water, put it onto the heater, and let it boil for 25 minutes. Yeah? And then after 25 minutes, you take it off, you empty your water, and then you serve your potatoes. That could be an open loop instruction for cooking potatoes. Yeah? And if you have the right size of potatoes and you're cooking at the right pressure level of air pressure, that means at typical altitudes here, then everything should be fine. If you are now cooking on a mountain, like say 4,000 meters high in the Himalaya, then your temperature with which you cook would be probably much lower, and you would probably have to cook your potatoes a bit longer. But you won't get that right if you don't do anything than following your instruction. And so the other approach, which is more like closed loop control, would be that you take measurements. So you say, cook your potatoes until a fork that you put into the potatoes doesn't, until the potatoes don't stick to the fork when you put it out again, right? So at the moment that your fork is just easily extractable from your potato, at that moment you stop cooking. Yeah? And that's a closed loop instruction, so to say. Closed loop, you would also say feedback. Yeah? So you use feedback. While open loop, you don't. And so this dividing line is particularly interesting for control engineers, right? So you can have control actions which are like, plan your path. And I think a lot of the activities that humans do are partially open loop and partially closed loop, right? So when I run, I have a plan of where I want to run, and I could close my eyes maybe for 2 seconds, and I can still run very well. If I close it for longer than 2 or 3 seconds, I will probably collide because I need corrections. Yeah? So there's a mix of the two things in practice. And in engineering also there are mixes. And I should say that the interesting thing I want to mention here is that in this class, even though practically closed loop control is very important, in this class our focus will mostly be about open loop optimal control. Yeah? And that is something that we can solve very cleanly and nicely. So we make a plan for a time horizon, what to do in order to get the best optimal result. So that's what this course is mostly about. And I should say that it's also used a lot in some techniques that try to design closed loop controllers. And in particular, if you use open loop controls and you repeat the optimization on a time horizon that always predicts a bit into the future, but then takes into account that you have an observation of your current state, then you enter the domain of receding horizon control or model predictive control. Or model predictive control. And then it's again closed loop control. And so basically it's the repeated solution of open loop problems that gives you some form of closed loop control. And that way we are also slightly treating closed loop control. I should say that there is the dream, so to say, of optimal control theory is actually the optimal feedback control. And this optimal feedback control is a form of closed loop control. Feedback and closed loop are nearly the same. And optimal feedback control is like the dream of lots of problems. It's typically applied to control systems which are time invariant, right? So for controlled time invariant systems, right? Time invariant systems. And I should say already that one answer to get the optimal feedback control is dynamic programming. That will actually address exactly this question. There's the so-called Bellman equation. But there are other answers, and MPC is an approximation of it, for example. So, I should say that the aim of optimal feedback control and all these feedback controllers are feedback control policies. So we call these policies, which are actually maps from states to controls. So it's a policy is actually what should I do if the state is that, right? For example, a policy is I should continue cooking if my fork still sticks, right? An open loop is actually, you don't have control policies, but you would have control trajectories. So we just call it a trajectory. And a control trajectory is typically something, if you have time here, and you have a time horizon from 0 to big T, it's something that could be cook for a while, then cook for another while a bit hotter, slow down your temperature and maybe stop cooking for the last 5 seconds or whatever. So this could be an open loop control. It's just a trajectory of controls u of t. It's just a function of t. Yeah? While here it would be a function u of x. That's a policy. Here it's a function of time. Here it's a function of state. This is, so to say, the big divide between closed and open loop. Yes, so what's the focus of our course? The focus of our course are deterministic systems in continuous state spaces and continuous controls. And we cover both continuous time and discrete time. And we will actually start with discrete time because it's a bit easier, and then move later to continuous time systems. You might ask, why is it so restrictive? Why is it continuous state spaces and continuous control spaces? Yeah? So let me write that down. So the focus of this course, continuous state and control spaces. And then obviously I should say that in finite dimensions. That means actually that x is just an element in R and x, and u is an element in R and u. And we will have discrete time and continuous time, xk, uk for discrete, and x of t and u of t in continuous time. Yeah, so that's we cover both, first discrete and then continuous time. And now you might ask, so why do we restrict ourselves to these continuous state and control spaces? And the reason for this is simple, and it's actually that they are much easier to solve. Yeah, so I should be honest about it. It's not because they are much more widespread than other classes. It's just because we can tremendously easier solve them. And in particular, we can use a derivative-based optimization. The reason can use derivative-based optimization. So the derivatives are the real thing. That's the reason. And derivatives are actually, Taylor series that tell you about the function, a nonlinear function, in a whole neighborhood of this function. And you need continuous spaces if you want to have a meaningful use of Taylor series, right? There is another reason which is closely related to that, and that is actually that it comprises the class of convex optimal control problems. Yeah. So contains subclass of convex optimal control. If you think of convexity, it's defined for optimization problems. It needs continuous decision spaces because there is this concept of a line between two feasible points, right? So you need to have all the points in between being also feasible. And so the same holds for convex optimal control problems. In this case, you need to have the concept of continuous, like convex combinations of two control trajectories must still be another a feasible control trajectory, and this is only possible if we have continuous control spaces. And actually the whole concept of convexity is also basically implying that the state space should be also continuous. Yeah, so we can have convex optimal control problems, which actually are those that are convex optimal optimization problems in either finite or infinite dimensions, but they will always be with state and control spaces being continuous. So that's the other reason. Yeah? So convex optimal control problems are so easy and so nice, but still so exciting and covering a lot of interesting cases that we will treat them a bit separately from time to time, and also a lot of the algorithms that we will later use for nonlinear problems and non-convex problems, they are based on the iterative solution of convex optimal control problems. And so that's why it's so important to think of convex optimal control. Yeah? So convexity is basically only possible if you have continuous spaces here. And that's why we have them. Thank you.